Okay, with the acid-base topics all now covered, all complete, I wanted to just recap and review a couple of topics that I feel like people tend to have trouble with, and they tend to all involve chemical equations, particularly chemical equations at equilibrium. So the first place where we see chemical equations with equilibrium are with weak acids and bases, and that's not usually an issue for people. This is probably the easiest of these topics. Like a weak acid, like ethanoic acid, you can show it with or without water, and when you show that it's a weak acid, you show it dissociating. And so in this instance, the equilibrium equation is meant to indicate that it only has partially dissociated, and the equilibrium heavily favors the reactants compared to the products. So there's a much higher concentration of the weak acid molecules than there are of the ions, which is why the weak acid is a poor conductor of electricity and has a relatively high pH compared to a strong acid of the same concentration. And the same applies for something like NH3, our common weak base. With this one, we would show it with water, show it acting as a proton acceptor, so we need to have something to give it a proton. That's the water, and I get NH4 plus here, and I get the OH minus. So once again, only partially dissociating, much higher concentration of ammonia than the NH4 plus and OH minus. So that's kind of the first place where we saw these equilibrium chemical equations that you should be able to come up with. Now, another important concept that relates to this is about conjugates and about relative strength. So remember that when we have these weak species, their conjugates have some amount of strength. So if this is our weak acid, then this is a conjugate base. And it's a conjugate base that does have some base character. It has enough base character to actually hydrolyze water, so to actually accept protons from water. So sometimes they want you to talk about, and I guess I wrote this the funny way, when I talk about conjugates, we also need to comment on their salts. So something like sodium ethanoate, we know is a basic salt because this ion came from a weak acid, and this ion came from a strong base. So overall, there's a basic character, and that's really because of this ion. And so sometimes they might say, explain why with a chemical equation, why this is going to be basic, or why the pH will be above 7 when you add this salt to water. And so if you're going to show that, you can ignore the Na+, that's a spectator ion. You could include it if you wanted to, but it's easiest to just show this ion on its own. And when you want to show something acting as an acid or a base, the simplest way is to show it reacting with water and doing the corresponding behavior. So if this is a basic salt, I need to show it accepting protons from water. It's going to be at equilibrium because it's very weak and it's only going to do this partially. So now it's going to turn into its conjugate acid, and it would also yield some OH minus ions in solution. So you can illustrate that this ion is basic by showing it reacting with water, accepting protons from water, and it also yields OH minus in solution. We know that if we yield OH minus in solution, that's going to make the pH rise. You could do the same thing with the NH4 plus. If you wanted to show how it would be an acidic ion, then you could show it in an equation with water. It's an acid though, so it needs to donate a proton to water. That's going to yield H3O plus and NH3. So they look a little different than the typical equations that you show, like up above here, these dissociation equations, but you should be able to come up with them. So keep that in your back pocket. If you're trying to display or illustrate acid-base behavior, the simplest way to do that is to show something reacting with water and illustrate either accepting or donating protons. Now it's a little bit different with the Lewis acids. If you're going to illustrate their character, like with BF3, if they don't specify, you could illustrate it reacting with a base. Like you could show it reacting with NH3, or you could show it reacting with OH minus, But you can also stick with that plan and show it just reacting with water. The key idea with the Lewis theory, though, if you're trying to illustrate Lewis theory, you have to remember that Lewis has to do with electron pairs. And if it's an acid with a proton, it was donating the proton. So with an electron pair, it's going to accept the electron pair to be a Lewis acid. So the key thing about these equations is, well, sometimes we actually show with curly arrows what's happening with the electron pair. Like we draw a curly arrow like that, like we did in organic chemistry, to show that we've got the B and the N are forming that coordinate covalent bond. And you could describe that, well, the BF3 has now bonded to the NH3, which was our base, so we've effectively neutralized the base. You can do it that way. If we're not asked to show curly arrows, then what we could do with water is, again, show a dissociation. First, you usually would show in the Lewis acid that it's bound up to the water. You might show it like that. And then we want to show that because water has bound onto this BF3, that water is now more likely to dissociate off additional protons. And we did this with transition metals too, so this is the same way you would show it with the transition metals. Now you've got BF3OH and H+. So it actually takes a couple of steps to sort of illustrate why BF3 is acidic. It's not immediately clear because it doesn't have any protons, but if you put it with the water can bond onto the BF3. That's what we show with this first product. It's sort of bound onto it with a coordinate covalent bond, and then one of the protons on the water is dissociated off, and so in the end, after two steps, we're showing that adding BF3 to water would actually increase the H+ concentration, and that would make the pH drop. So not maybe the first thing that comes to your mind. I feel like people kind of freeze when they get a question like this. They say, illustrate with a chemical equation how BF3 would lower the pH. And you just kind of freeze. Well, if it's going to lower the pH, you have to show how it creates H+. And if you want to illustrate acid-base character, the kind of most applicable way to do that would be applicable across lots of different questions, would be to show it reacting with water and to show that character that way. A couple other ways that we've left here with indicators. You've got indicators typically should be thought of as these weak acid molecules, and you can kind of just summarize their structure like this: H bonded to IN, and they just reach equilibrium like other weak acids do. And then you need to be able to describe when they would turn what color. So the key thing is that you've got color number 1 over here, and you've got color number 2 over here. If you add H+, you should know that's going to cause a shift left. And when you shift left, the concentration of IN- will go down. This color 2 will basically disappear, and you'll be shifting left, so you'll be making a bunch of the HIN, what's on the left-hand side of this equation. So you're going to see this color when you add acid. The color of HIN is what you'll see in acidic solutions. And if you add OH-, you're going to react with H+. You're going to effectively remove H+. That's going to cause a shift to the right. That will cause the concentration of IN- to go up. It will cause the concentration of HIN- to go down. And so you're going to end up seeing color number 2. So you can use equations to describe the stresses and the shifts and how that would affect the color. And then the last one is buffers. The buffer one, you really just show the weak acid dissociation equation if you're dealing with an acidic buffer, like this. The difference, what makes it a buffer, is that both of these things are now present in almost equal amounts, or possibly equal amounts. That was described in a previous video. And so now with this buffer, you should be able to describe which direction it shifts when you add acid or base. So adding acid is like adding H+, shift left, and that removes H plus because it reacts with the CH3COO minus. If you add OH minus, that will react with the H plus, and then it will shift right to replace H plus. When the CH3COOH dissociates apart, it's going to make new free H pluses. And so in both cases, the pH remains largely unchanged because the H plus that you added can be removed and the H plus that is lost can be replaced. So those are all different ways that equilibrium equations come up in this topic, and they're really important to be familiar with because it's pretty common for them to ask you to illustrate a concept using chemical equations. And I think these ones, they could freeze you in your tracks, and I don't want them to. So hopefully this video has helped clarify a few things, and we can answer questions when I'm back.